The fantastic aspect of Stable Diffusion is its capability for customization. It can't generate images for virtually anything, but the real magic happens when we train it to produce visuals exactly as we envision. Let's explore how to personalize its outputs to fit our unique tastes. One of the simplest and most effective methods for doing this is text inversion. It's even more straightforward than LoRa training, and the great news is it doesn't require a high-quality dataset, making it ideal for beginners. The training process shares a lot of similarities with LoRa training, so mastering text inversion can give you a solid foundation and make it easier to tackle LoRa training later on. And yes, just like with LoRa, you can train it to replicate any face or generate any portrait you desire. Now, you might recall seeing quite a few tutorials on this topic about a year ago. However, the automatic 1111 has evolved since then, which might lead to some confusion. Plus, there have been some innovative approaches to working with datasets that have emerged. This is why I felt compelled to create a new video to provide you with a thorough understanding of text inversion, right down to the principles. In this video, we're going to focus on training with a photo of the renowned Hollywood actress Angelina Jolie. Now, you might wonder, why train an embedding for Angelina Jolie when Stable Diffusion already knows what she looks like? Here's the thing. While Stable Diffusion has been trained on 600 million publicly available images, not all of these images are of the highest quality, nor do they necessarily match our personal mental image of Angelina. By selecting our favorite photos to train with, we can create a version of Angelina that aligns with our own vision. That's the real power of training. Take a look at these before and after training images. On the left, we have the original Angelina, and on the right is the Angelina I've trained. The difference is stark. In the following sections, I'll walk you through the entire process of training and embedding on Angelina Jolie, covering everything from data set preparation and image pre-processing to the actual training and evaluating the outcomes. To help you grasp the concept better, I'll delve into some foundational principles throughout the training process. These principles are akin to those used in training both LoRa and DreamBooth, underscoring their significance in grasping the overarching methodology. Before we kick off the training, it's crucial to prepare our data set, the collection of images we'll use for training. This step is super important as it directly influences the quality of our final output. Think of it like cooking. Just as high-quality ingredients are essential for creating a delicious meal, high-quality images are necessary for producing outstanding results. Let's ensure we have the best ingredients before we start. There are two key principles to adhere to. First, prioritize the quality of images over quantity. Second, ensure diversity in your images. This means including a variety of angles, expressions, and backgrounds to give the AI a well-rounded understanding of the subject's characteristics. For training models for portraits, it's advisable to have at least 10 facial images. Including some full body or upper body shots helps the AI learn about the person's body shape and posture. Remember, the images must be free from watermarks to prevent them from appearing in the final generated image. Let's look at some examples I've generated using datasets of varying quality. On the left column, the images were produced with a lower quality dataset, and you can see the difference compared to the right. Notice how the eyes in this photo don't look quite right. And these two photos, they're suffering from a significant amount of overexposure. However, the image on the right, it's a marked improvement. The contrast between these images, especially the ones below, is strikingly evident. Once our images are selected, the next step involves pre-processing, which includes both cropping and captioning. It's essential to crop the images to a uniform resolution for optimal results, with 512 by 512 being the ideal size. Fortunately, there are several automated methods available to streamline this process. In previous versions of Automatic 1111, the Pre-Process Images feature was located under the Train section, which is where the training process takes place. However, in the latest version of Automatic 1111, this functionality has been removed from the Train section. For batch processing images online, I found a particularly user-friendly website, and I'll include the URL in the video description below for easy access. Upon visiting this site, simply click on the Browse from your computer button to open your file browser. Navigate to your designated folder and press Ctrl-A to select all the images you intend to pre-process, then click Open. You'll notice that the cropping areas for these images are automatically highlighted thanks to the preset width and height dimensions. The Auto Detect Image Focal Point option should already be selected for you. This feature allows you to preview the cropping and make any necessary adjustments to ensure accuracy. For instance, if this face is inadvertently cropped out, I can manually adjust the cropping box. For this image, I need to move the box slightly. Also, this one. After making these adjustments, hit the Save as Zip button to compile your images into a zip file. Choose a save location, and your batch of images will be neatly cropped and ready for the next stage of the process. Next, let's tackle captioning the image. As mentioned earlier, Stable Diffusion was initially trained using 600 million images, each accompanied by captions. This rich dataset is precisely why we're able to generate images through prompts. Whether employing text inversion or LoRa techniques, captioning the image, adding descriptive prompts to outline what the image represents is a crucial step. Navigate to Automatic 1111 and switch to the Tagger tab. This tool is an invaluable extension for Automatic 1111, streamlining the captioning process significantly. If it's not yet installed on your system, check the video description below for a link to get it set up. You'll find it equally useful for captioning during LoRa training. Click on Batch from Directory to begin. Here, input the path to the images we're looking to process. Since I'm running Stable Diffusion on a server, the path format might differ from what you'd use on a personal computer. Adjust the path to suit your setup. There's no need to specify this output directory. By default, the tool saves the generated caption file in the same folder as the images being processed. Next, choose a model from the Interrogator drop-down menu. For processing portraits, ViTe-V2 comes highly recommended due to its effectiveness. There's an option to adjust the weight threshold. Lowering this threshold results in more detailed captions, but be prepared for an increase in irrelevant captions as a consequence. This, naturally, may lead to a greater investment of time in caption modifications. Let's fine-tune this setting to strike the right balance between detail and accuracy. After configuring the settings, hit Interrogate and wait for the captioning to complete. This feature also displays the frequency of tag occurrence, offering insights into the commonalities within your dataset. Upon navigating to our dataset folder, you'll notice quite a few text files. These files share their names with the corresponding images. Opening one reveals the interrogated prompt already present. However, refining these captions is advisable. The more precise they are, the more effective the text inversion training will be. To streamline caption modification, we'll leverage another extension, which I'll link to in the video description below for easy access. After installation, switch to the Dataset Tag Editor tab. Our first order of business is to load the image alongside the newly generated caption. Enter the path for both the images and captions into the text box under Dataset Directory, then hit the Load button to the right. A moment later, scroll down. We can see the images from the specified folder. On the right, the extension conveniently displays tags associated with these images. Selecting a tag filters the images containing that specific tag, simplifying the process of identifying and modifying relevant captions. Now, how to refine the captions? The process is a bit counterintuitive. Take, for example, Angelina's lips, a distinct feature of hers. You might assume that including the word lips in the captions is essential for the AI to recognize and replicate this feature accurately. However, that's not necessarily the case. The truth is, we can't fully capture the essence of Angelina's lips through mere words. AI, much like humans, learns more effectively from visual inputs than textual descriptions. Consider this. If you describe the thickness and shape of Angelina's lips to a painter, can they replicate it accurately without a visual reference? Probably not. Similarly, AI depends on images for learning detail features, using text primarily as a means to receive commands from us. I hope this clarifies the somewhat nuanced approach needed when refining captions for AI training. Now, let's explore how to efficiently manage tags within our dataset. Start by clicking on this tag to determine how many images include this specific tag. As you can see, we discover 16 images, indicating the need for a batch deletion. To proceed, scroll up and click on the Batch Edit Captions button. This feature is divided into three useful sub-functions: search and replace, remove, and extras. Since our goal is to remove a tag, we navigate to the Remove tab. Here, the Remove Selected Tags option becomes available. Scrolling down, select the Lips tag for removal and then click that button. In moments, the tag vanishes from the tag list within this interface, though it's not entirely gone yet. The Lips tags still exist in the text file within the folder. It's merely hidden from view in this context. To permanently remove the tag, you'd typically click the Save All Changes button found in the upper left corner. However, it's wise to postpone this final step until after completing all caption edits, providing a safety net for any potential oversights. The process also applies to other specific terms that may require bulk deletion, such as breasts, nose, and brown hair. Conversely, certain terms, especially those related to the background, like white background, should be retained to prevent the AI from erroneously linking these background features with the subject, in this case, Angelina. It's possible to select and remove multiple tags simultaneously for efficiency. Additionally, for less frequent tags, individual editing is an option. Select an image, for example, this one, then access the Edit Caption of Selected Image feature adjacent to Batch Edit Captions. This action brings up the caption for the chosen image, allowing for manual editing. For instance, removing the eyelashes tag and applying the changes to that specific image showcases the flexibility of both batch and single edit functionalities. After thoroughly reviewing and editing the image captions, the final step is to click Save All Changes, securely applying all modifications to the dataset. After refining the captions, we've laid all the groundwork necessary to begin training. However, before we dive into the training phase, it's crucial to adjust some basic settings to ensure everything runs smoothly. Let's navigate back to Automatic 1111. Click on the Settings tab, scroll down to locate the Train section, and click on it. Then, scroll up to fine-tune a few essential settings. Here's my recommended setup. The first option should be enabled if your system is limited by video memory. This helps manage memory usage more efficiently. The second option boosts training speed, but be aware that it will consume more memory. Enable this if memory isn't a concern for your setup. The third option is particularly useful as it creates a backup file in your training folder. This allows you to pause and resume training without losing any progress, thanks to this backup. The fourth option is usually enabled by default and can be left as is. The subsequent options are generally not necessary for basic training and can be left unchecked. The option to save a CSV containing the loss to log directory every n steps is set to a default of 500 steps. You might consider lowering this for more frequent updates, which can be useful for closely monitoring the training's progress. We'll delve into what loss means in a bit. Leave the other options as they are. After configuring these settings, click Apply Settings and then Reload UI to refresh your interface. With these settings adjusted, we're now ready to proceed to the Train section and start the actual training process. To kick off the training process, click on the Train button, which brings you to the training interface. The initial step in training is creating an embedding. Selecting an appropriate base model is pivotal. It's recommended to opt for 1.5 base model for achieving broad applicability. This choice ensures that your training benefits from improved generalization capabilities, allowing the customized embedding to work effectively across various other models built on the 1.5 base model, yielding satisfactory outcomes. It's crucial to note that SDXL models should not be selected for this process, as doing so will result in errors. If you're lacking a 1.5 base model, refer to the link provided in the video description, which directs you to Hugging Face, where you can download the appropriate model. Opt for this model, it's the superior option. Initiate the download by clicking the download button situated to the right. However, this model is larger, and you can get good results by choosing this one above. For the VAE setting, the best option is to select None. Next, you'll need to give your embedding a name. This identifier can be anything you choose. For instance, I've named mine AJ. So what is this name and embedding? To clarify these concepts and other parameters you'll encounter later, I've recreated a diagram which is created by a Reddit user. This visual aid is helpful to demystify the underlying principles of text inversion, making the process more accessible and understandable. As we all know, humans navigate the world through natural language, employing words like AJ to interact with AI. However, AI doesn't grasp language as we do. Instead, it translates these words into continuous vectors within a high-dimensional space known as embedding. This embedding reflects the pattern of pixel distribution in an image, essentially how the AI perceives and understands visual information. We've initiated an embedding named AJAJ. At this point, AJAJ is merely a label for an empty vector space that awaits definition through training. The aim of this training is for the diffusion model to process this embedding and recreate Angelina's appearance as depicted in our training dataset. Consequently, when we input AJ into the prompt post-training, Stable Diffusion will generate an image of Angelina closely resembling the training images. During this process, Stable Diffusion undertakes two primary actions with the training image. First, it converts the training image into noise. The embedding captures this noise pattern, which Stable Diffusion then partially denoises to produce an initial representation of Angelina. Second, Stable Diffusion deconstructs the training image to establish a regular pixel distribution, enabling a comparison between this distribution and the initial Angelina representation. This comparison yields a loss value, quantifying the discrepancy between the two versions. A higher loss indicates a larger difference. Utilizing this loss value, Stable Diffusion iteratively refines the embedding, enhancing its accuracy with each cycle. Consequently, the initial version of the image generated based on the progressively updated embedding increasingly resembles the training image. Simultaneously, the loss value decreases, signaling a narrowing gap between the generated and training images. This iterative process continues until the embedding optimally represents the training image, culminating in a highly accurate embedding. Now that we've grasped the core concept of text inversion, let's circle back to the train interface. When it comes to naming your embedding, it's somewhat flexible. However, it's advisable to avoid using names already present in the base model, such as Angelina Jolie. The reason isn't about triggering errors, but about our goal to train an embedding from the ground up. Incorporating Angelina Jolie as the name could inadvertently lead to training on the pre-existing base model version of Angelina Jolie, which isn't our objective. We aim for the AI to learn from the specific images we've curated, ensuring that the resultant Angelina closely mirrors the characteristics in our training dataset rather than reverting to the generalized version found in the base model. Therefore, it's best to leave the initialization text field empty to prevent Stable Diffusion from defaulting to its base knowledge of Angelina Jolie in the initial training steps. Moving on to the parameter number of vectors per token. What does it mean? Let's revisit our diagram for a moment. Let's say AJ is a token and the one below it is the vector relationship with it. A higher count of vectors per token allows for a more complex representation, potentially capturing more nuances of Angelina's features. However, in practical terms, this setting doesn't drastically influence the outcome. Typically, setting it to 1 or 2 can achieve good results. This option is usually not mandatory to adjust. If you find the initial embedding unsatisfactory and wish to retrain, you can simply delete the prior embedding and start anew. Once you've configured the parameters to your liking, clicking Create Embedding will initiate the creation of an empty embedding. You'll see a notification confirming this action, signaling that you're ready to proceed with the training. Once we've successfully created our embedding, it's time to move on to the training phase by clicking on the Train button, which takes us to the interface where we can enter our training parameters. Make sure to select the embedding we've just created from the drop-down list. If it doesn't immediately appear, click the refresh button on the right to update the list. There's no need to adjust settings like hypernetwork learning rate, and gradient clipping, as these pertain specifically to the training of the hypernetwork, a more advanced concept that's not our focus here. The critical parameter to consider is the learning rate, which essentially dictates the pace at which the AI learns or the speed of training. Imagine training as sculpting. A high learning rate initially acts like a sledgehammer, quickly chiseling out the rough shape of a Buddha statue. As the outline becomes clearer, switching to finer tools or lowering the learning rate allows for more detailed work, leading to a polished final product. The learning rate strategy I'm adopting was inspired by a suggestion from a Reddit user. It involves a dynamic adjustment of the learning rate throughout the training process. Initially, from steps 1 to 10, we apply a higher learning rate of 0.05 to quickly establish the basic features. Then, the learning rate decreases to 0.02 for steps 10 to 20, and further reduces to 0.01 for steps 20 to 60, continuing to adjust as training progresses. Beyond the 3000th step, the learning rate is set at a minimal 0.05, maintaining this rate until the training concludes. This approach to adjusting the learning rate is designed to be more effective across a broad range of datasets. It contrasts with the default setting of a constant learning rate of 0.05, which, while generally effective, might not finely tune the model's learning as the training advances. In my own experimentation with this dataset, I found the impact of this nuanced learning rate adjustment to be noticeable, though not dramatically so. The batch size parameter functions similarly to the one used in the text-to-image feature, where increasing its value can speed up. However, setting it too high risks overwhelming the video memory. To counterbalance an increased batch size, it's advisable to also adjust the gradient accumulation steps accordingly. The interplay between these two settings is intricate, so unless you're specifically aiming to maximize training speed, sticking to the default values is generally recommended. Next, you'll need to specify the path for your dataset. As I'm running Stable Diffusion on a server, the directory structure may differ from a standard local setup. You can adhere to the default setting here, which automatically generates a folder in the root directory of Automatic 1111 for the training data. For the prompt template, I've opted for a customized approach. Automatic 1111 includes several pre-designed templates, and for portrait training, the template named Subject File Words is a fitting choice. These templates reside within the Textual Inversion Templates folder in Automatic 1111's root directory. One of the contents of the Subject File Words template looks like this. I found much of its content excessive for my training needs, leading me to create a streamlined version. This revised template retains only the essential elements: name, file words. Here, name refers to the embedding's name, AJAJ in this instance, and file words corresponds to the image's caption. For example, if a training image's caption is looking at camera, the prompt, according to our template, becomes AJAJ looking at camera. This refined prompt then guides the diffusion model during training, illustrating the template's significance. It's important not to adjust the image width and height settings below the prompt template section. After configuring these settings, simply scroll down to proceed with the next steps in the training setup. One crucial parameter to pay attention to is max steps. This parameter determines the maximum number of iterations the training process will undergo. Let's revisit our earlier diagram to deepen our understanding. As previously mentioned, training is an iterative process. Initially, there's a significant difference between the image generated from the original embedding and the one derived from our training dataset, resulting in a high loss value. Stable Diffusion then adjusts the embedding based on this loss, aiming to minimize the differences in subsequent training rounds. Max steps sets the limit for these iterations, while the default is set to 100,000. Achieving satisfactory results typically requires only around 3,000 steps. Setting this value too high may lead to overfitting. For instance, if Angelina is known for her distinctively full lips, an excessive number of training steps could exaggerate this feature to the point of distortion in the generated images. However, there's flexibility as training can be halted at any point, preserving the last saved embedding. This allows for the selection of an optimally trained embedding without the concern of overcommitting to a high max steps value. Another parameter: save an image to log directory every n steps, 0 to disable, controls how often Stable Diffusion saves a progress image during training. A smaller number here lets you observe the training effects more frequently, providing insight into the model's progression. Similarly, the adjacent setting enables frequent generation and saving of embedding iterations, useful for refining and selecting the best performing version. This is an option we generally don't check. Although it will speed up the training, it is more troublesome to process the dataset and change some other parameters. This option, save images with embedding in PNG chunks, we can check. Enabling this feature allows for the creation of preview images throughout the training journey. These images are conveniently saved in the Image Embeddings folder and are tagged with the embedding's name alongside other relevant details. The Shuffle Tags by Comma when creating prompts option is worth enabling. It randomizes prompt positions in captions, ensuring each word within the prompt maintains consistent influence over the image generation, potentially enhancing embedding quality. Lastly, regarding the sampling method, While the official paper typically references random sampling, the community has introduced a deterministic method, offering an alternative approach to training. Once you've configured these settings to your preference, clicking Train Embedding initiates the training. This process is flexible. You can pause and resume without compromising training quality, thanks to the earlier step of enabling backup file creation. All right, folks, once we kick off the training, don't forget to scroll up a bit. Over on the right, there's this preview area where we can keep an eye on how things are shaping up. This progress bar gives us a heads up on how far along we are in the training journey. Now below that, there's a bunch of info. Remember when we chatted about the whole concept of text inversion? That's where this loss value comes into play. It's like a score that tells us how well the training is doing. Then there's the step, which counts the training steps we've taken. And there's more, like a recap of the last prompt we used, the latest embedding we've saved, and a sneak peek of the image. Speaking of images, the one we're seeing in the preview, yep, that's the one we were talking about earlier. But here's the deal. It might not look much like Angelina Jolie just yet. Early on, these images can be a bit rough around the edges, sometimes literally, with stuff like wonky hands or feet. That's because we're still using the base model without any fancy prompts to amp up the quality or cut down on the glitches. But here's where the magic happens. As we keep training and then use our shiny new embedding with other models like realistic vision, the images will start looking way more like Angelina, smooth, detailed, and just plain stunning. Once we hit pause on the training or wrap it up, we get to check out how our embedding turned out. Over in the text inversion folder, sorted by date, that's where all our hard work pays off. Even though I'm running this show on a server and things might look a tad different than on your home computer, the layout's pretty much the same. Inside the date named folder, you'll find the embeddings folder, where our trained embedding awaits, neatly named and ready to show off its skills. I've configured it to produce a new embedding every certain number of steps, resulting in a collection of embeddings. Each embedding's name includes a number indicating the training step at which it was generated. With an array of embeddings at our disposal, determining the most effective one might seem daunting. To assess which embedding performs best, start by reviewing the preview images stored in the Image Embeddings folder. These images, labeled with their respective embedding names, provide a preliminary basis for evaluation. Once you've identified a potential range of effective embeddings, transfer those of interest to the Embeddings folder within the Automatic 1111 root directory. This enables you to generate and compare visual representations of these embeddings directly in Automatic 1111, offering insight into their real-world application. Indeed, I've previously showcased several comparison charts, all created using the approach I'm outlining now. Within Automatic 1111, select a base model for testing. Realistic Vision is my choice, though you might also consider a 1.5 base model for versatility. Input your prompt based on the embedding step of interest, such as AJA J500, for an embedding generated after 500 steps, leaving other and negative prompts optional. Proceed to the Scripts section at the interface's bottom, where you'll select XYZ plot from the drop-down menu. The options for X-axis, Y-axis, and Z-axis within this script setting might initially be confusing, but their purpose becomes clear upon reviewing the final plot. This final plot serves as a visual tool for comparison, where the X-axis, the horizontal axis, displays the sequence of embeddings, each labeled by the specific training step at which it was created. The Y-axis, or vertical axis, corresponds to various prompts that I've designated to represent different hairstyles. This organized visual representation allows us to directly observe how Angelina's appearance, particularly her hairstyles, varies with each step of embedding. By examining this plot we can effortlessly discern which embeddings produce the most accurate or aesthetically pleasing versions of Angelina, with various hairstyles facilitating an informed selection of the optimal embedding for our specific needs. For example, in the first photo, we used the embedding of step 500 and the prompt of wavy lob to generate the photo. Alright, now that we've grasped the significance of the x-axis and y-axis, let's dive back into Automatic 1111 to further explore how to generate this insightful plot. Navigate to the X-Type drop-down menu and select Prompt Search Replace. In the X Values field, input the names of the embeddings you wish to evaluate, such as AJ, AJ500, AJ, AJ1000, AJ, AJ1500, and so on. The Prompt Search Replace feature essentially allows for the dynamic substitution of these specified embeddings into the prompt for each generated image, enabling a systematic comparison across different training steps. For instance, if your initial prompt includes AJ500, this function will replace that segment with the comma-separated values you've entered for the x-axis, generating images with AJ500, AJ1000, AJ1500 sequentially. This setup offers flexibility in defining the interval of steps you're interested in exploring. Moving on to setting the y-axis, you have various options at your disposal, such as seed or CFG. However, sticking with Prompt Search Replace again, you can input descriptors related to hairstyles or other variables of interest separated by commas into the y-axis field. It's important to ensure that the values entered do not conclude with a comma to avoid errors. After configuring your axis, hit the Generate button located at the top right to start plot creation. Be prepared for this process to take some time. Patience is key. Let me accelerate this part for efficiency in our walkthrough. This preliminary testing phase allows for an extensive exploration of different variables, aiding in the selection of the most suitable embedding. While text inversion stands out for its simplicity compared to other training methodologies, it's worth noting that its outcomes are somewhat limited by its nature. In future discussions, I'll delve into training with Laura, which shares many principles with text inversion, enriching our understanding of these training techniques. Thank you for your patience and engagement. If you found this video helpful, I'd appreciate a few clicks of support. Stay tuned for the next episode.